Good morning, everybody from Oslo. I'm looking at the participant list here, and we've got people from all over the world, it looks like. At least somebody from the west coast of Canada. Welcome to our presentation from Geodata. My name is Joel Waltner, and I will kick things off here this morning with my colleagues. We think we have a pretty exciting agenda for you this morning. That we hope will give you some things to take with you in your journey with FME. Yes, they have a number of different presentations on different topics, from using Strava data to do some exciting things, how FME is being used for snowplows, for airports, and for creating a countrywide database here in Norway. A little bit about us, Geodata. We are a SAFE software, a gold partner. I've been a partner with SAFE for many, many years. We are also the Esri distributor here in Norway. Have customers in every different industry, many different industries, all kinds of different things with GIS. We are about getting close to 150 employees, spread out mostly in the Oslo area, but we have an office in Stavanger on the west coast as well. And most of those are consultants doing GIS work in different companies. Today we will go through, we have 5 different presentations. They all last about 15 minutes each. And we'll just go from one to the other, and then we'll have room for questions at the end. Just say that we are not marketing people. We're not presentation experts. This is actually the first time any of us are using Zoom. So we hope this all runs smoothly. And if there are any hiccups, blame it on this technology people not understanding this new technology for us. We'll give a few more minutes to make sure everybody who wants to come in gives a chance. I'm just saying we start with Nils, Juell, who will be doing a presentation about data gravity and using principles implemented in high volume solutions. From there, we move on to Erik Dyve, who is going to do a presentation about tracking snow in the city of Oslo. From there, we move on to Knut Olav Sunde, who has been working on a GeoNorge project for many years, lots of expertise there, and will present some of the what's going on behind the scenes. And from there, we go on to something a little bit more fun, perhaps, with Francesco De Biasi, who's done some work to play around with some of his Strava data to see what kind of exciting things we can do there with a GPS map. And we'll wrap things up with Morten Grimnes, who will be showing us how the Norwegian Airport Authority is updating their central database for messages and Eurocontrol. And I think with that, we will go ahead and move on and start our first presentation. Nils, you can take over.
Thank you, Joel. So I will talk today a little about something called data gravity and how to process high data volumes in FME. So my name is Nils. I work for Geodata in Oslo, and I've been an FME user for 14 years, so quite advanced and senior, I would say. My current assignments are in the telecom industry, where I've been working for the last 3 years on a huge project on data integration, and also in the construction industry for data preparation for some special apps that we use. I'm also the coordinator for Geodata's internal FME focus group. So data gravity, now, what is that? As you all know, FME is a very good tool for handling data flows, but sometimes streaming data through FME might not be our best approach. I will show you how to utilize FME in a different way. And this principle is called data gravity. So today I will take you through the definition of it, some explanations, application tips, pros and cons, and finally 4 examples on how to implement it or run it. So there are many definitions about data gravity, but like from the main seem to be that data gravity is the ability of a body of data to attract application services and other data. So maybe this is a little too passive definition. So translated into Don and Dalish, as I have observed with several occasions, saying something like data operations should run close to the source. So this is an interesting principle, as SAFE implicates that FME is not always the best tool for every task. So I give them some kudos for this transparency. It's very good. However, we will still utilize FME as an orchestrator for these principles. And I will try to explain what I mean now. So the traditional FME design is something like we have our data, which we access through something in the generic term called an access system. So this can be of type storage, read, write, or functions, or other things. And examples on these are an operating system you use to access your files, for instance. DBMS like Postgres or Oracle or whatever, ArcGIS, you have some Excel functions, you have a lot of other examples on this. And we have our beloved FME, that we run the desired operations and the data flows from the system to FME and back again, for instance. Now, there is a cost here that can be illustrated with the gravity of the data. So to simplify this for our case, let's say data gravity is the sum of access time, of startup delay, suboptimal functions, transport cost, and more. So we want to reduce these costs, and by slightly different design, we use FME to send the access system commands so that we do our operations directly on the data. I hope that was fathomable. Now, so when do we apply this? As I said initially, it's not always that FME is the optimal tool, and it's not always that data gravity is the optimal tool either, but it's a little list on how to select which ones to utilize here. So to me, the principle has shown fortunate when I have like a big data flow, or I have repetitive tasks, or I have access system tools like SQL or commands that are supreme to what you find in FME. So they do the tasks quicker or better in a way. And when you should not apply it, definitely, is when you're trying to do a proof of concept, then FME is supreme. You just put all your functions together and you see if something works, and you kind of get the result that you want, very visually powerful. Or if you have very complex data flows, then it might also be very cumbersome with the data gravity to apply it. So we have some pros and cons, just to drag you through this as well. For the most importantly is the speed, that you will gain significantly speed improvement on this. You will gain some simplicity. That's a nice reward. It's not always desired, as I put on this little asterisk here. It might be so simple that you really need to document thoroughly in FME what happens remotely, as it might be difficult to trace and find otherwise. I mean, you obviously run commands on a different system, so you need to tell the user what's happening. You will also get rid of your load on your local system and put it on the remote system. This can be a pro or a con, but let's say that in our case it's a pro, because you might have a DBA that don't like these things, that you put a load on their different computer, like a remote server where you run your database, for instance. So the cons is that, let's say you cannot use your normal FME thinking. You need to have thorough knowledge of the remote system, and you have less control of the load that you actually put on this remote system. It might not be a remote system, it might be your local file system. So maybe you still have control, but it's a little fire and forget thing, so it might hit you back, so be aware of that. And now I'll move on to our examples here. It will not be a demo, it is more like just examples that I will talk around. So this first one is just to illustrate that the power of data gravity. It's a very simple task that you can do in you just want to list all the files between two dates. So the classic FME, you put up your file reader like a path reader, you format your input dates so that you can later match it in the tester and compare the dates that they are in between a certain interval, and then you list the results. So typically this can then take 2 minutes to do. Now with a PowerShell command that you just kick off with the creator, you make it in the prepare the command in an attribute manager. Then you run it in a system caller, and it takes 1.3 seconds because everything runs on the file system. You don't read any data into FME or back again. Our next example is a little similar in the simplicity, at least. So we just want to read some files and do some features and do something with it. So it doesn't matter where you read from, but let's say it's about 23,000 objects that comes in, and then you filter and you're left with 195. And with a little calculation and filtering, this takes about 2 minutes. It's not a very complex test. So how can we do this faster? Some of you might be doing this unaware already. So you use the where clause on the reader with the same filtering, and as you can see, you have the same amount of features coming out, and you start your transformations. So it's a significant gain here. Then we have an example where you want to enrich your data from other sources. So our main data flow starts on the top left here, like the previous example. And then we want to add on some attribute values from the two other readers here. So we use merge, test, filter, etc. It can be a more complex thing, but in the end, we see that we are stuck, we're just left with 23 features, and it takes like 13 minutes to run this thing. So again, how can we? I mean, it's hundreds and thousands of features, and how can we do this faster? So the key here in the data gravity, as it is implemented here, is that you need to prepare your data store. Of course, that has a cost to it, but if you run this like repetitive tasks, as I touched previously, and you have quite huge data amounts, it is a significant gain. So typically with indexing and some writing of some SQL code, like this example is Postgres, you do all the operations and the enriching and joining and filtering in the where clause. So here we choose something called work order ID that will be included in a selecting. So this select is basically what replaces all our previous transformers. So we go from typically 13 minutes to 4 seconds, and that is very valuable. The only thing you need to is that you need to remember to expose your new attributes here. That's very important because if you just add your reader like this, you will only get listed the its native attributes from that table, but you are adding on more attributes, so you need to list them, expose them. And our final example here is XML wrestling. In classic FME, you go through very often some cumbersome design to handle your XMLs because it exists on many levels, and you get huge workspaces. And this is from just an excerpt from one of my projects in the telco. So how can data gravity help us here? It's a different approach than the others because we start with XML. So how do we do this? Well, basically, we read XML into Postgres tables raw, like text fields, or you can actually tag them as XML data type. But then you need to be aware that you have to remove all file references, or else it will fail. So you need to clean up the XML a little. If you store it as text, it's just as text. So that's very easy. So then we use like a first step FME to extract attributes and create our attributes by running an SQL directly on the table. And the key here is that you use the XPath function to extract the values, so that you will actually have a very improved data source that you can operate on in a very much easy way. And this is much faster than to let your data stream through a whole FME workspace. But this about wraps up my presentation, so I will hand it over to Jan Erik.
Thank you, and thank you for the presentation, Nils. I'll just share my screen. Joel, I think I have some technical issue getting my screen shared.
Okay, try again. Are you able to now, Jan Erik?
Yes, thank you. Can you see my screen now?
Oh, you're okay, yes.
Yeah, thank you. Okay, good morning, everyone. My name is Erik Dyve, and I work as a consultant at Geodata AS. I've been there for about 3 years, and during that time, I worked quite a lot with FME. Now, for the last 2 years, I spent my time at the municipality of Oslo's Agency for Urban Planning, and there I worked on a project on tracking plowing machines together with many talented people. And I'm very happy today to be able to share this with you, audience. Just a few facts about Oslo. It has Oslo is the capital of Norway with a population of 697,000 people. It covers just around 454 square kilometers, and most of that is actually forest. But we do, of course, have a lot of roads, and that's kind of the main actor in this presentation. We have 1,240 kilometers of road and about 1,000 kilometers of pavement and bicycle lanes. And of course, we have a lot of snow, which needs to be done with during snowfall. The story behind tracking is based on a need for better control on how money is spent on winter operation. Each year, this costs the municipality about $30 million US, so 300 million Norwegian crowns. And the political level wanted to have a closer track on the use of this money. For the administrators overseeing this operation on a daily basis, this information gives them a better insight in not just the cost, but also the operational performance. And it also improves the more informal communication between the contractors and the administrators because they both have access to the same information. And it improves the quality of the information passed to the public. And the plans are that in some years, this will actually be shared with the public on websites. We also seen that this data can be used to estimate the environmental impact that the winter operations creates each year. All in all, tracking this machine is an important part of a step towards smarter cities. So this is the hero of my presentation. It's a typical example of a plowing machine. In Oslo, when there is a snowfall, there's about 250 of these machines doing their work with approximately 300 people in action. They come in different sizes. This is probably a medium size. You have the large ones on the large roads, and you have small ones on pavements and such. These are, of course, equipped with snow removal equipment. This one has a brush, which is probably not that common, but it is often used instead of the more traditional plow. And this machine also has a salt spreader behind to dispense salt to prevent from creation of ice. On this tractor, there is a central processing unit, a CPU, which collects the data from sensors located inside these two equipments. The sensor, they register if, for instance, the brush is up or down, indicating that it's actually doing work. And the dispenser has a sensor which registers if salt is being dispensed and the amount. And in addition, this CPU tracks the speed of the vehicle and the location through a GPS receiver and other data as well. And all of this data is then transmitted to a central server where it is processed further. And this is where FME kicks in, because the FME service is set up to pull the data from this server every hour and does some initial analysis, and then it stores the data in an ArcGIS Enterprise Geodatabase. The data is then made available in a ArcGIS server, and this provides map data to other applications. And on your right side, you can see a picture, which I actually took from my office window, home office window, where you can see the tractor doing some work. And below, you can see the same track left by this tractor. So you might actually note that the tracks are not actually quite perfect. They have some uncertainty and so on, but overall we get a picture of what has been going on. This figure shows a general outline of what is done with FME. There are 3 steps that are run in sequence. The first step is basically just receiving the data from the server. And this is received as point data. So for every point, there is, of course, the location and the time step and the information on what was done in the by the machine. And here we use the HTTP caller to get this information. In step 2, lines are made between each pair of points. So you get a line, and this line represents the distance that the car moved, and will also contain whatever activity was done during that period of time. And for this, we use the line builder. And the final step is basically just aggregating continuous lines based on the unique ID of the machine and the activity. So if the machine was plowing for, let's say, 1 kilometer, this will be shown as one line. And if it then continues to salt, then that will be shown as a new line. And for this, we use the line combiner transformer. But in addition, we have a quite nice system for controlling the flow of the data, because one important thing with our solution is that we really need to make sure that most of the data is actually kept, that we don't lose anything. So for every step in the process, we tag the timestamp and use this to make sure that if something fails, it can be continued on the next run. So we do one hour sequences, so we do the process every hour, and this actually helps us to improve the quality of the data by making sure that we always have control of what data was actually processed. This is an example of the performance of the solution. It shows the number of points that were collected during the last season from September 2020 until 14th of April this year. And you can clearly see the periods where there is a lot of snowfall. And at the most, we collect about 22,000 data points per hour from all the vehicles that are out doing snow plowing. Note especially this on 11th of March, because I will now show you a demonstration of how it looked like. So this is just from the end users tools. They have selected the specific date, and here they can filter on different activities, types of work like plowing, or they can look at salting and kind of get the impression of where was these activities performed. They can also zoom in on the map and get some additional information about that specific track. So what is shown here is these aggregated data. And they can see the mileage and the average speed, the usage of salt, and so on. And here's also an example of a statistics report that they also have access to. They can show on the left side the number of vehicles that were active per hour during this snowfall. And on the right side is a view of how many kilometers were performed for each type of work and the total. So this is very useful information for the administrators at the agency when they want to monitor the work and also get an understanding of the cost. Now, the questions that they asked was, okay, so we know where the machines are working and we know what they did, but was it done on time? And which road did they miss? Now, this was it done on time is an important factor, because by contract they must clean specific roads in a certain time limit based on when the snow started. So I think if it's 5 centimeters of snow, then they have to clean that road within 1 hour. Roads with less priority, they might have to do it in 3 hours and so on. So we kind of want to make sure that we know if they did the work on time. But also we want to know, well, what did they miss? Because if you remember the map from my previous animation, it was kind of clear to see where they've been working, but what about the roads that they should have done something with and which they missed? One challenge is that this is quite a lot of data and we want it to go efficiently as possible. So we did some work on how to optimize this type of analysis, where we want to get an overview of both the timing and the overall performance of which roads were managed. So our solution is what we internally call the Pac-Man method. And you probably understand why we call it that in a minute or two. So the main principle is that we take the road network of Oslo and we use the snipper to create points for a selection of these road segments. Now, these road segments are categorized by the priority that they have. So, for instance, main roads will have high priority, then local roads and so on. And cycle lanes have a high priority also in Oslo. So if you use the snipper with a 50% snipping on each side, we end up with a point. But what we also do is that we create a grid of 250 by 250 meters. And this is just a method to reduce the number of road segments that we are looking at, because initially it's 40,000 segments, but during some testing, we found that the performance wasn't that good, because we want to make sure that these analyses run within a fairly short time. So we use these grids to, together with the point on area overlay, to reduce the number of segments that we are looking at. And the reduction is actually just done with the duplicate filter, because after applying which zone the segment belongs to, we only pick one for each category of roads that we are looking at. So this does actually reduce the number of segments into about 1/10, 4,000. And so these actually kind of represents all the roads that we expect the contractors to clean during snowfall. Or put another way, these are the roads. We pick some and apply these points. So this is where Pacman comes in, because it means that the snowmobiles will eat these points while they are driving around and doing the work. One benefit with this solution is that it's much more simpler to actually identify which track belongs to which road, because if you look at this map now, you can in some cases see that some lines might actually cross roads they did not at all touch, and by using the points, it's much easier to do a spatial spatial intersect between the points and the lines, and get the right road. So when we plan to present this to the user, and I should note that this is still work in progress, they will get a data set and can give them the fraction of the city roads being cleaned at some given time after snowfall. And they can also get an indication of which areas did not get cleaned at all or were delayed. And they can get an indication of if prioritized roads were actually cleaned on time. And for the first point here, during heavy snowfall, the administrators need to talk to the media to tell the people what is the current status on the snow cleaning, and then they have kind of easily access to say that, well, at this moment, 58% of the city has been cleaned. That was the end of my presentation. Thank you for your attention, and then I leave the floor to the next presenter.
Juell, will you please make me the host?
You are the host, Knut Olav. So you should be able to share your screen. Get things started.
Sorry. Now. Hello everybody, my name is Knut Olav Sunde and I'm working as a senior GIS advisor for the Norwegian private company Geodata AS. I will tell about the data distribution in the Norwegian national geoportal GeoNorge and how FME is used to automate the data flow behind the scenes. As a consultant, I have worked with our customer, Norwegian Mapping Authority, to develop the data distribution through GeoNorge for the last years. To set things in a perspective, I will give you some facts about the data distribution through GeoNorge. A total of 416 datasets from 33 different data owners are distributed through the portal. A central distribution database and more than 440,000 downloadable files in a variety of formats are kept continuously up to date. The main engine behind the scenes is FME, delivering massive data processing and data distribution through download services and other OGC-compliant online services. We have now moved to the geoportal geonorge.no itself, and I'm now displaying the main page of the map catalog, where I can search for data sets and present metadata for them. I will search for a particular data set, data, that is actually depth for nautical charts. Here we have the metadata available for that data set. I can show the coverage of the data. So here we can see exactly which area has objects in the data set. I will go to the download center and pick two different geographical areas. I will pick Oslo municipality, the capital of Norway. That's available as a pre-produced file in UTM-32 coordinate system and GML format. I will also select a special area directly from the map. So I zoom into the map and I select a small area around these islands here. Like that. So then I have two different areas that I want to order. The municipality of Oslo and a small area selected directly in the cart, in the map. The municipality is accessible as a pre-produced file, and the area that I selected will necessarily be produced on demand. I have to add my email address, and then I can just download the data. And now it's processing and will be returned to my email shortly. I have now received an email from geonorge.no that is containing a download link to a zip file containing the two files that I ordered, the municipality of Oslo and the area that I picked in the map. I have now downloaded my file and we can open it, and we can see that it is a package containing the two different files that I ordered, the pre-produced file of the municipality of Oslo and my area of interest that I picked directly in the map. I have now unzipped the file with the area that I selected in the map and just drag it into this map. So here we can see my GML file displayed directly in the map. I turn off a few layers here to make it better visible to you. So here is data directly accessible to use in this tool. And now we will look a little further into what is running behind the scenes, doing all the processing that is necessary for the GeoNorge data distribution. The main components are FME desktop and FME server. FME desktop is used to import data on a regular basis from a variety of data sources, files, databases, and services. FME desktop is also used to keep the more than 440,000 pre-produced files up to date. FME server is used to deliver the same content as files produced on demand, and also to deliver atom feeds. FME desktop is automated using the Jenkins open source automation server. A PostgreSQL PostGIS database serves as a data hotel in between import and export. Currently, the data distribution in GeoNorge consists of more than 2,400 FME workspaces that is running on more than 30 servers. The data distribution in GeoNorge is fully model-driven. Product specifications are developed as UML models in the tool Enterprise Architect. From the UML model, there are exported scripts and parameter files used to configure the readers and writers in FME, and also to create empty schemas in the distribution database for the data sets. There are also exported application schemas for GML export. Now we have moved to FME to show a typical import of data to the distribution database. This is again the depth data for the nautical charts. Data is here read from an Oracle database and is forced into the schema defined by the product specification created in Enterprise Architect. And finally, everything is written to the database. As you can see here, it's several object types. We have now moved to the distribution database. We can here see the empty schema created in the PostGIS database using scripts exported from the UML model in Enterprise Architect. The FME job for FME is to fill these empty tables with data. And after the process that we just saw, the table has been filled with the data according to the harmonized product specification that was created in the UML model. And we can even look at the different objects and their geometry placed in the map. We have now moved to the web user interface of Jenkins, the automation server that is automating the import of data and the export of pre-produced files in GeoNorge. What we can see here is a list of jobs that can be run on a regular basis. Right now, we can see down here that the import of depth data from the Oracle database to the PostGIS distribution database is running. We can open it to see a little bit more. You can see that it has currently been running for 2 hours and 19 minutes, and we can see that it is running once a week. After the import is finished, then the export phase will start. We are now back in FME to see how export of data is happening. In this export workspace, we can see that it is a set of parameters that's controlling the output. These parameters are 100% standardized across all data sets and all formats. This parameter setting that we see here will produce municipality number 301, which is Oslo, and it's set to produce municipalities and in UTM 33. Based on this parameter setting, there will be made a clipping polygon in this transformers here. It is sent to the feature reader as an initiator to read only the data that's in the area of the clipping polygon, and it's also sent to the clipper to clip data. Based on that, the data is mapped to the, in this case, GML specification and exported to GML format. The workspaces for export is made in such a way that they can be run both in a FME desktop environment and in a FME server environment. For export of pre-processed files, it's important just to export those areas, municipalities or counties that has been affected by changes in the data since the last export. That is done in this huge workspace, and basically it's using spatial SQL to query the PostGIS database to see if there has been imported any objects that has been updated since the last import. If so, it finds the municipality numbers or county numbers that has been affected and exports them. The export itself is done using workspace runners that actually makes it possible to run several exports in parallel. So it can run up till 7 parallel FME processes on one FME desktop license. As we can see here on one of the application servers, we can see that several FME processes is running simultaneously, each of them exporting a particular file. We have now moved to FME server, and we can see here in this repository workspaces, export workspaces published as data download services. They can be used by the users to produce files of their area of interest on demand. We can move down and find our depth data again. Here it is. And with this has the same parameters that's also used in desktop for massive file production. In on-demand production, either coordinates are added as such from the clicking in the map, or it is produced a Clipper file that's uploaded as a resource and used by the service. And after a while, the user will receive the data exported. FME server is also running a set of service jobs to assist the portal to deliver data to the user. One of them is the file packer that's packing together several of pre-produced files or files produced on demand in a large zip. And we have also a service job that checks orders, and when they are completed, the status and download link is posted back to the portal using the GeoNorge REST API. For all datasets and format combinations, there are published atom feeds as data streaming services on FME server. So that makes files accessible as for download through an RSS feed. This RSS feeds is also used by a desktop client that can massively download data and keep a copy of the data synchronized on the user's side. We have now come to the end of this presentation. Before that, I will just summarize my presentation a bit. FME's software is an ideal solution to develop effective and flexible data distribution to a geoportal like GeoNorge. Data processing with FME desktop can be automated and parallelized with various tools to obtain a maximized data throughput. FME server is an ideal platform to serve fresh geographical data on demand. And then it's just left to say thank you so much for your attention. Don't hesitate to contact me if you have any question about what I have presented here today.
Okay, welcome to this presentation. That's other windows here. Okay, right. My presentation is about making a customized GPS map for Garmin device based on Strava heat maps or Strava tracks. Just quickly about myself, my name is Francesco De Biasi, and I work as a GIS consultant for Geodata in Oslo. I like traveling, hope to do it again soon. Spend time with my family and cycling, which is one of my passions and one of the subject we're talking about today. So we will have a quick look at Strava, what is it, and how I use this tool to plan my bike routes and send them to my Garmin GPS device for tracking and navigation. We look at some of the challenges we have when we use a map for navigation on trails or paved road, and why I came up with the idea of making my own map. We see how FME can help us to do the job quickly and clean, how to make the workflow. Then we'll see very quickly how the map creation process. Just a quick look at what Strava is. Strava is a tool, a web tool that allows users to track and analyze every aspect of an activity. It's been growing a lot during the last years. It allows to connect with friends and share your adventures and be inspired. That's one of the reasons why Strava is called the social network for athletes. You can record an activity and it goes right to your Strava feed, and your friends can like it, comments, and yeah, it's very social. You can the best part of Strava though is that you can explore new routes and compete with the global community using, for example, segments that are some stretches of road or trail, and Strava create a leaderboard of times set by every Strava athlete who has been there before. And this is very popular, especially now that it's been not possible to arrange races and meet physically. So it's a very, very good features. It's been using a lot now. Yeah, it's a say that if it's been run or ridden, then it's on Strava. That's what we say. So there's millions of athletes all over the world. So the Strava road and trail network is unmatched. So heat maps give you a look at popular roads ridden by people all over the world. So it's a very good tool when you want to explore the map and build your route. You can also build your own heat map. So what I do, I usually plan my route using heat map and then send the file automatically to my Garmin GPS. The thing is that the GPS is a Garmin Edge. It's very good GPS and for monitoring performance and turn-by-turn navigation. This GPS come often pre-installed maps with, or you can download the map from OpenStreetMap, for example. But how does it work when you follow a Strava route? Sometimes it works just fine. You just find a nice path that is rideable and it just match with the Garmin map. Other times not so much, so it's can be quite challenging. At the same time, there is no specific map for cyclists, so you don't have the information about surface, or if you have, it's sometimes it's not real. It's not doesn't match. And the other problem is that these maps they are quite difficult to read on a small device has a GPS. They contain a lot of information. So I started wondering why not making my own map based on my Strava activities, my local map. I can definitely get some information of the type of road, based on the bike I used, and the data is accessible from an API. And I also have prior experience in building GPS map for Garmin. So let's see how I get the data processed. First thing is to establish a Strava web connection that makes possible to access the API. This is very well explained in the setup instruction windows and the FME. So very easy to connect to Strava. What I do is that I read my data using a looper transformer, because I pull up 30 activities at a time. In this case, we filter data by date. So I, when I run the workspace the first time, I just pull the last 2 years data just to create base and master data. And then when I want to update the map, I can just limit the search for the last 14 days, for example, and then update it. So this is how I read the data, is a custom transformer. And next step is to filter. I want to create a local map, so I just select those activities that has the starting points nearby home. I simply create a point and create a buffer. I use a spatial filter to do the selection. I also want to filter the activity by types, discarding all activities that are not of type ride, like running, walking, cardio, etc. And of course, I also discard commutes. They are all the same. Next step is to get a detailed geometry for each activity. So you need to call the Strava API one more time for each of the activities. And you get also an attribute which is called gear ID, which is the attribute that say which bike has been used for the ride. I have two bikes, one a race bike and a gravel bike. So I can use this tag to describe the surface of the road. The point is that if the gear ID is a gravel bike, so the road has a gravel surface. If the gear ID is a road, is a tarmac, and if it's both, then we assume it's tarmac. The next step then is to we get all these lines here. What we want to do now is to merge these lines in order to create a single line, but at the same time keep track of the type of road. So to do that, we create a buffer for the center line, for the lines, and we aggregate by type. So we can use this to identify the surface type. We also run dissolve on buffered lines and create center lines, and we intersect them. So here are our center lines here. So now we are ready to test the relation and assign the road type to each line segment based on the attribute in the list. And to do that, we use a spatial relator. And here we have a line which has a list attribute, gravel. So we say that that line has a gravel surface. So if it's one relation, it's just one road type. If we have two relation, which means that the same line, each line segment can be written by two activities, then it's say it's tarmac.
Hello.
This is how the model for road type assignment looks like. at the end of this, we just reproject the data, and we write to shape files, which is the format required by the Garmin map creator software. At the end here, we have the system caller that call the bat file, which launches the executable for the map creator. The executable just contains the bat file with the path of the program and the configuration file. Very quickly regarding the creator program, it's a Garmin program that we have been used for some project at Geodata, and what we use it, how we use it is we simply load the shape files as input. You can configure the look of the map, and what I used in this case was the Strava roads created with this workflow. Then I had some water features that are good to recognize the map, like lakes and river. Then I had some cities, and then I picked up some N50 roads and assigned them a very light symbol just as background, since I don't have all the roads on the map. So this program just convert this map and create an EMG file, which is the format that Garmin use. So this is the result that I have on my map and on my GPS, and I think this looks a bit cleaner and easier to read, especially when I'm in the middle of the woods and I need to find which tracks to pick up, just not to carry my bike so long. Yes, that's what I had, and thank you. I can take some questions later on, and yeah, that's next one is Morten.
Thank you.
Bare vent litt, jeg må bare sørge for at det blir en glidende bra overgang når du bytter folk her.
Can I start? Hi, my name is Morten Grimnes. I work as a senior GIS consultant for Geodata AS in Norway. I will give you a brief presentation on writing AI XM 5.1. This presentation is based upon a project that I did for Avinor, and Avinor is a wholly owned state-limited company under the Norwegian Ministry of Transport and Communications, and they are responsible for 44 state-owned airports in Norway. Avinor needs to send updated aeronautical information to Eurocontrol in AIXM 5.1 format. Messages are sent from a centralized system, which is wizard by Indra Avitek, which communicates with the outer world either through a GUI, an AXL query service, or AIXM 5.1 files. The contents of this database is automatically or manually updated from surrounding specialized systems, like for instance, reference points. I will take a look at some of the hurdles we had transferring data from the reference point system's objects positions to wizard by using the AIXM5 format. Before we go any further, it's important to realize that the AIXM 5.1 is a complex object format. Position is just a tiny part of an AIXM objects for those objects that actually contain a position. The AIXM 5.1 object definitions are expandable through the use of extensions. And Avinor has utilized extension to a high degree, adding even more complexity to the AIXM 5.1 object format. So what part of the AIXM 5.1 object do we update? This is a visual representation of an aircraft stand. And as you can see, there are quite a lot of attributes there. Now, the information that we have in the reference points system is the little part which is marked in yellow, which we can see is just a tiny part of the complete object. And the data from the reference point systems can update what's called an elevated point in AIXM 5.1. We came across a couple of hurdles while we're working on this project. And the first one was that we found out that to update the position of an AIXM 5.1 object, we need to send a complete AIXM 5 object to update Wizard. Otherwise, other attributes that were in the object would be lost. The interface to Wizard from FME's point of view is through an AXL query service, which in turn returns AIXM 5.1 objects. So to simplify the use of the AXL, we ended up adding a front end to Wizard's AXL service, which we call Wizard Query, which contains methods that are tailor-made for transferring reference points. The workflow we envisioned when we started this project was that we receive a GML export file from the reference point system. This is a standard GML file. This file is fed into FME, and FME reads every object from the GML file, and with the help of the Wizard Query frontend, we are able to transfer this to AIXM 5.1 objects. These objects are written to a file and they are sent to the Wizard database, which in turn reads that AIXM 5.1 file and imports that into its database. The steps we need to take in FME to fulfill this workflow is roughly this. I need to read the export file from the reference point system, one object at a time. For each object that I read, I need to search for the object in the Wizard database through the use of the frontend we call Wizard Query. If I find the object in the Wizard, then I use that information and store that information with new updated point information and make what's called a AIXM 5.1 perm delta message. If I cannot find the object within Wizard, then I need to create a new object with basic attribute values to be stored in the Wizard database. This is what in AIXM 5.1 is called a baseline message. And at the end, I write all the objects that I've found or created new to the AIXM 5.1 result file. Now looking a bit into FME to see what happens when we have read one object from the export file. As I said, we need to search for the object in Wizard, and the custom transformer at the far left is where I perform this action. And this, as I said earlier, can result in two different results. I can either find the object within Wizard or I do not find the object within Wizard. And that states what the source for my AIXM 5.1 object is when I read that into the workspace with the feature reader at the far right. If I find the object, then the object itself is stored in a file and used as a source for the feature reader. The only thing left for me to do is to specify the message type and define that the temporary file that I've stored the AIXM 5.1 object from Wizard is stored as the source for the feature reader. If I haven't found that, I resort to reading the object from a file containing a copy of each object type with predefined standard attribute values for each of the objects that I am sure to encounter when I'm reading from the export file. This example is an aircraft stand, and an aircraft stand needs to have a reference to the apron on which it is placed. So when I haven't found the object, then I actually have to look for the apron and put that into an X-link within the AIXM 5.1 object. Having found that, I specify the message type as a baseline message, specify the baseline file where the objects are stored as a source for the feature reader, and then I read the objects through the feature reader. When reading an AIXM 5.1 object, we need to know that the object contains of two parts. The first is the object itself, or what's called a container object. This is the object that actually refers to the object and has the unique key for the object. The second part is what's called a time slice. A time slice is the temporal part of an AIXM 5.1 object, and it's also the time slice that holds all the attributes values for the object. So when reading an AIXM 5.1 object, we need to read both the container object and the time slice. For the container object, we need to set the GML ID, which is the reference to the object itself. We need to set the reference to the message heading, which is a part of the AIXM file, and that's put in the GML parent ID. And we also need to set the GML parent property to has member. Now this is defined in the AIXM 5.1 definition. For the time slice, we need to set the GML ID for the object. This is an internal GML ID and is not used to refer to the object itself because that's referred to in the container object. We also need to reference the object itself. So we need to put the GML ID that we used in the container object in the GML parent ID attribute. And we need to set the GML parent property to time slice, which is also defined in the AIXM 5.1 definitions. The last thing we need to do before writing the time slice is that we need to replace the current geometry which we have read from the AIXM 5.1 object with the new geometry that we've read from the export file from the reference point systems. So the first thing we do is that we remove the existing geometry of the object. Then we start by adding a new vertex, and we set the geometry name to the correct value, which for points is location. We add the necessary geometry traits that are defined in the AIXM 5.1's definitions, and we add those to the new geometry. And for Avinor's part, we also need to add a geometry extension or elevated point extension, which is created to supplement the attributes of what's defined in the AIXM 5.1 definitions. What have we achieved by using FME to transform the standard GML export file from the reference point systems to the AIXM 5.1 file that is being imported into Wizard? First of all, the positional data for the reference points are delivered electronically from the surveyors and imported into the reference point system. These positional data are for the reference points are transferred to the Wizard database electronically from the reference point systems. The positional data from the surveyors are safeguarded by a CRC value that is calculated by the surveyors And this CRC value is used when importing the same data into the wizard database to ensure that no data has been altered since being delivered from the surveyors. So there is no human interaction on positional values when receiving them from the surveyors and storing them into the wizard database. And this adheres to the aeronautical data quality regulations. What have we achieved during this project? Well, by using FME, we are able to transform simple objects from a GML export into a full AIXM 5.1 objects by leveraging the possibilities in FME to attach to several different data sources. Since AIXM 5.1 is one of the formats that FME supports, managing AIXM 5.1 within FME is really straightforward. And last but not least, this project has gained me an insight into the challenges that AIXM 5.1 may pose. And with that, I say thank you, and thank you for your participation.
Thank you, Morten, and thank you to the rest of my colleagues for their presentations. I see there's already come in a couple of questions. We have about 10 minutes. So if, Francesco, I don't know if you've already seen the questions, but maybe you can take a look and answer them, or if the people who are joining us from other places want to jump in and ask the question live, they can do that.
Yeah, okay. The first question from Glenn. If you have plans to make it possible for other users to add to your database or for other people to access the data that you have created. At this stage, I just been playing around with my account and basically just because if you need to give you need to allow permission and give permission to access the Strava API and the Strava account. If I have time and I like to play around with these things, so it should be possible to create an interface where people can give permission to run to access the API and run the workspace. But I haven't looked at it. This possibility yet, but I've seen other people has done the same before. So you can basically you need a system that allows the user to give permission and run the workspace on their own data. So the other question with the trail map concept. Yeah. I don't know that, but yeah, it's basically that crowdsource the road and path surface quality. Yeah, we have something like this in Norway. For example, there's some forum that are very popular amongst mountain bikers. There are some services you can look at and get detailed information on the surface. Like Strava is more general. It works both for road type, for road bike and gravel and mountain bike. But if you look at some specific mountain bike website, so you get some more information and more detailed information. So definitely it's there are a lot of sources out there. For me, it was like a way to make a very easy map to read on the GPS without all the things that makes confusing. I can still add tracks and trails when I ride them, and so I used to plan new roads and new tracks from this website, and then when I ride it, so I can implement in my map or discard them if it doesn't work. So yeah.
Great.
I hope I answered the question.
Thank Mark, you and Glenn for your questions. Any other questions? Okay, if not, then we will say thank you to everybody.
There's one question.
Is there another question? Yeah.
To Erik.
Was there a question to Erik? Image providing the public with snow plowing data. Any plans on opening up the snow plowing data via an open API?
Good question. I can't really answer. No, but I will bring it along. Yeah, I think that will be my best one.
Thank you. Yeah, well then we will say thank you for everybody who has joined us from different parts of the country, different parts of the world. We hope that you enjoy the rest of your World Fair, and hopefully we can meet live again in maybe next year. Great, thank you.